Assalamualaikum. So today's we have a fifth or last lecture of the webinar of lecture series Optical Forces on Atoms, and our guest speaker Dr. Saif is here with us. So I invite Sir for the lecture. So thank you.
Well, Assalamu alaikum. Today it is the last webinar of our 5 webinar series. So I start with submitting my thanks to uh, 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 Professor Dr. Iqbal Chaudhry Saab for his keen interest in the project, in my book, and also inviting me for the 5 webinar series. I also thank the supporting staff of Comstech who had made this possible to to arrange this webinar series in an amicable way. So many thanks. So in these webinars, we have tried to understand the basic tools, concepts, and mathematical terminologies which are used in these discussions, which takes us towards the quantum technologies at hand today. So this is a very beautiful subject. It has matured over the last 2 decades. And what we say today is an enormous flux of numerous devices which are coming to our everyday life. So these devices are making our uh, life and work simpler. For example, in case of quantum computers, which are very much there on the door. And then we have a very important, interesting innovation, which is coming uh, very fast towards us, and they are in the form of some nano devices, nano structures, quantum mechanical technology, engineering, and so on and so forth. So what we have seen in this uh, series of webinars that the techniques we developed are namely for atoms using optical force. But we can generalize these discussions towards macroscopic objects like cantilever and membranes. And at the same time, we can apply these discussions towards ions and molecules as well. So this is a very big area in which we can generalize our these present discussion. So, so we have dedicated one webinar to a macroscopic system and the control of macroscopic system using optical forces. So that was our topic of discussion yesterday. So I would very much encourage my audience, my uh, uh, participants, that if they want to join our research projects, they're very much welcome. So we have uh, uh, theoretical work, numerical work, analytical work going on in all these experiments, which are very well connected to the latest technologies. So, um, so okay. Now, I'll open up today's discussion by presenting the application of the optical forces on atom as kind of quantum technologies at hand. And the one very important thing comes as quantum computers based on ultra-cold atoms. So this is one of the technique with which we are trying to develop quantum computers. The others are like quantum computer based on optical photons and ions and so on. So here we have uh, our ultra-cold atoms, which are being used to develop uh, uh, quantum computers. So the advantage with ultra-cold atom is that by using the changing profile of optical fields, we can develop traps which can hold our alto-gold atoms very precisely. And you know very well, these traps are discussed in our discussion as optical tweezers. So they can be macroscopic devices, which can be used to trap alto-gold atoms. And these arrangement can be made as large as thousands of atoms being stored at various different, using thousands of optical tweezers at the same time. The advantage is that the alto-gold atoms have coherence time around 12 seconds, which is very, very far for any quantum application when we want to work with the qubits and apply logic gates. We can control these atoms with the optical fields in our discussion. And the large coherence time is a very big advantage to develop these atom-based the quantum computer. Here, another option can be using ions. So if we, instead of alto-cold atoms, we use ions, and then we require Paul traps, which are again can be a very beautiful arrangement, and we can store again thousands of ions in those traps. So these are possibilities which we can have in our discussion. Another very beautiful discussion is atom gravitometer or atom gravimeter. Sometimes we say it. So here you have seen in our previous discussion that once atoms are placed in the optical lattices, they they simulate the semiconductor materials in our discussion. But it is very interesting to see that if we have these alto-gold atoms falling under gravity, and then we apply the optical lattices in the vertical direction, the energy spectrum changes entirely. For example, in case of atoms in an optical lattices, we find the energy spectrum is following the energy band diagram, which is there for anything like electron in a crystal. So there is a very good comparison. But as soon as we have the atoms, they are under gravity, and we apply the optical lattice, for example. So it is optical lattice in the presence of a linear potential. So just the addition of a linear potential changes the energy spectrum. So now our atoms are going to see an atomic spectrum which is equally spaced. Now, equally spaced energy spectrum is seen in very good examples, in very good textbook examples, where we have, for example, harmonic oscillator. That's a very good example of equal energy spacing spectrum. So similar thing now is made in a completely different environment. And in the environment where we have optical lattice in the presence of a linear potential. But the advantage is that now our energy spectrum is equally spaced energy spectrum. So, so if you want to have a schematic diagram of this kind of optical lattice, we may have this simple structure that it is periodic, but is following the gravitational potential and having a linear tilt. So that is a simple, interesting thing. So the atoms which are stored at the potential minima, they can hop. They can hop from one potential minima to the next potential minima. So this is something which we see. Now, this hopping, which is happening under gravity, is going to be interrupted by the equal spacing of energy spectrum. What it means in simple understanding, what we should think of that atom under gravity should just fall due to in the gravitational field as a free falling object. Under gravity, So, but in the presence of the gravity, these equally spacing energy spectrum can be written as mh bar omega, where omega is fd by h bar, and F is the force applied on the atom, and it is calculated simply as mg. So this is the simple expression for the frequency. Now, the presence of frequency in the gravity in the presence of frequency in the presence of gravity in the frequency has consequences in the later dynamics. So what we see that we apply the optical pulse in we apply the standing wave field for a time, and then we switch it off, let the atoms move freely, and then we apply the standing wave field again, and then let them move again freely, and then we apply it third time. What happens in meantime that the application of the first pulse is going to introduce Bragg deflection. And we were discussing Bragg deflection in our previous discussion. So Bragg deflection is going to introduce a superposition. It can introduce a superposition if it is applied for a certain controlled time. This we were knowing. And then it can serve as a reflector or a deflector. It can deflect the incoming atoms completely if we apply for another time. So this happens up here, that if we apply this, if we let the atoms fall under gravity, we let the atom fall from a magneto-optic trap, not shown here. So these atoms are just falling under gravity, and then we apply a standing wave field, which is acting like an optical pulse. So this optical pulse shining on these atoms for a certain time acts like a beam splitter due to the Bragg deflection. And these deflected atoms move with two different momentum. So it is in the momentum space all happening. So and then we apply this optical pulse again, and the time is doubled from previously, and that makes the atom deflect. And then we combine these atoms again by applying a pulse of pi/2 interaction time. So this makes a Mach-Sender interferometer. So the change in the angle due to the gravity change can be measured on the screen after the interference phenomena. And that change in the angle of if there is some gravity change would be giving us a value of the G, which is going to be the modified G for the system. So this becomes a simple mechanism for an atomic gravitometer. And then we were previously discussing the role of ultra-cooled atoms in developing microscopes of very high resolution. So this discussion is very useful, and we can develop scanning probe microscopes of various different kinds. So I introduced previously that we have scanning tunneling microscope, we have atomic force microscope, but they have their own disadvantages. Atomic force microscope is an all classical device. It's not a quantum mechanical device. Scanning tunneling microscope is a quantum mechanical device, but it is based on the tunneling current. So that can be used only in the scenario once the specimen is conducting. And second thing, if it is having anything like impurity, it would be giving a false information. So to avoid these deficiencies, we introduce another completely different recurrence tracking microscope, which is based on the quantum mechanical principle of quantum revivals. So we let the Broglie waves fall on an atomic mirror made by the optical field, and this atomic mirror reflect back the incoming atoms or de Broglie waves. And so the incoming atoms and the reflected atoms interfere with each other and change the spatial profile. So space-time behavior is changed. So they just show an interference phenomena. So this is a larger picture of this recurrence tracking microscope. So we have a magneto-optic trap. Atoms fall under gravity towards the atomic mirror. They reflect back from the mirror, and then they interfere with each other. And due to the interference, we see two options. Either it is constructive interference or destructive interference. So in the beginning, the destructive interference takes place, and that kills the wave behavior in the evolution, or and then we see the interference pattern is destroyed because of destructive interference, and then in quantum mechanical domain we observe that the destructive interference is followed by the constructive interference, which takes the initial, which brings the initial wave packet back into its original place in the original shape. So this is the advantage. So that time, once it is available at the original place from where it started in very much the original shape, we say it is a quantum revival phenomenon. So that time is important for us. And this time, quantum revival time is now having the information of the initial height of atoms above the atomic mirror. So that means that if this distance changes, the time of revival will change. And this becomes a principle of our recurrence tracking microscope. So this takes us to calculate the time of revivals with changing uh, distances. And from the change in the time of revival, we understand the information of the surface structure down here. Very easy to picture that if the cantilever, which is above the surface structure, is seeing some atom, it will move up, and then that will reduce the distance of atom and the mirror, and that will be reducing the time of revival. But if the cantilever is not seeing any surface structure, that is, there is no atom on the surface, it will go down. That will take the mirror going down and increasing the distance between the atoms and the atomic mirror. So the increased distance per quadrant would be seen as a increased time of revival. And the difference in the change in the time of revival will give us the information of the change of the surface structure down there. So this becomes a very simple mechanism. Okay, so this is one way of choosing this device, which is named as recurrence tracking microscope. We can use this in a different way as well. So this is something which is very much similar to STM and AFM, because we go point by point in STM and we go point by point in AFM as well. But if we already know that we are having a periodic structure at hand, which we want to study, for example, we have a biological tissue, biological sample, which is periodic in nature. So then we can just move this surface with a slight movement, and that will be making this cantilever go up and down periodically, and that will make this atom fall on a mirror, which is performing a surface movement. So it is just like a ball falling on a moving hand, or a ball falling on a moving racket. If you move the racket up and down, so then the ball will gain some energy sometime and will lose energy some other time. So system becomes high dimensional, as we were discussing yesterday, and by nature it will be a complex system, a chaotic system. Now that simple, that microscopes Okay, so let's come back. So we have uh, we are discussing the recurrence tracking microscope. So I was just presenting that this particular device, which we named as recurrence tracking microscope, can be used in static mode, which is very much the same uh, we observe in STM or AFM. We go point by point on the sample and scan it. But it can also be used in a dynamical mode where we can read our surface in a much faster way. So that you can find in the book as well, what is the intricacy with that particular dynamics. So it is requiring some better mathematical handling, which I'm not presenting for sure here. And then it's requiring some more parametric controls. So that is an advantage in the dynamical mode. So, well, using ultra-cold atoms, we are in a position to develop atom lasers, which is very big excitement and very big goal once we have lasers with us. So lasers are made up of photons, and photons are bosons. But these photons are made up are particle which describe light. Fine. So in case of lasers, we have photons which are coming one after the other in a very coherent manner. So we have space coherence, we have time and space, we have spatial coherence and temporal coherence. So it is in time and in space. So as soon as we have uh, bosons, photons as bosons, and they're presenting lasers as a coherent source of light, there is immediately a competition coming, a challenge coming, that is it possible that we can develop lasers with the help of bosons, which are basically matter, atoms. So these ultra-cold atoms can act like bosons, like bosons and condensates. And the only thing is that is it possible to develop lasers from them? So laser would be simply a coherent source of matter. So using our ultra-cold atoms, it is possible to have uh, atom lasers, which is very good discussion, good point of discussion. We can have pulsed atom lasers and we can have continuous atom lasers. So in pulsed atom lasers, we can visualize very simply that if we have a trap in which we can develop condensate and we store the condensate and switch it off. So the stored atoms would be falling under gravity and will be propagating in a coherent fashion because they're at a cryogenic temperature, at nanokelvin temperature. So they will, before they heat up and lose their coherence, they will be following the coherence dynamics and they act like a, atom lasers. And in the meantime, our trap is switched on again, and it is again storing another condensate. And at a later time, it will be switched off, and another pulse of atoms coming and falling on anywhere we want to do anything. So this is one way of saying we have atom lasers, but in the pulse form. In the requirement of a continuous atom laser is definitely there. We want a source, we want a mechanism, we want a way to have a continuous propagation of atoms, uh, and we can use it for anything we want to. So that can be obtained by using as it is named as, it is using a hot wire in the trap. So we bring a hot wire, so that hot wire will be making the atoms boil down, but still at very, very low temperature. So these boiled down atoms would be now propagated coherently and in a continuous manner. Okay, so this is uh, so this is something we can say as pulse atom laser I just introduced, and then we can have continuous atom lasers if we introduce this hot wire in this. Now that hot wire can be something like a optical fiber, which we were discussing yesterday, and that optical fiber would be still able to trap atoms in the radial direction. So this is something very interesting that we can introduce an optical fiber which is able to trap our atoms in the magneto-optic trap, but still only in the radial direction. But these atoms trapped in the radial direction can be propagated along the axis of the fiber due to the field present propagating inside. So this will be so interesting thing is that the trapping would be along the radial direction, but along the axial direction, which is axis of the fiber, the propagation of atom may take place. Because if it is a propagating field inside the fiber, it will provide an h bar k kick on the atoms along the axis of the fiber. So that would be useful to take our atoms from a condensate to any place we want to take in a coherent fashion. So this would be making a laser which is all the time coming from the trap, and we can use it as a pen or anything we want to do. So it would be depositing the matter in a controlled fashion as per our requirement. So this can be one way of visualizing an atom lasers. So this is something which is quite useful. So we were discussing in our previous webinars that it is possible to use atoms which are coming, propagating in a particular direction, and we place standing wave fields in front of these coming atoms and develop scattering of these atoms. So that gives us a good opportunity to spread the atoms in a controlled fashion if we want, and then refocus them again at a later stage as per our requirement. So we can develop various different kind of masks with the help of atoms directly, like if we use a diffraction grating from these in front of these atoms. So this is a direct deposition of atoms on a surface as per our requirement. So this is something which is quite fascinating. So, well, we were discussing that in our webinars that once we have atoms interacting with the optical lattices and the atomic temperature is being lowered and lowered, so they start observing, appreciating the periodicity of the lattice. And at that time, we can see them being trapped in the optical lattices, or and they can be manipulated for any particular thing. Okay, so this periodic optical lattices and the ultra-cold atom trapped in them open up the subject of solid-state physics and condensed matter physics for the laboratory purposes. And for that matter, we can do all the things which we do with ideal crystals in these atom optical lattices. So this is a very good advantage, but the scale is very large. So we can do we can observe all those effects happening at a very large scale with the help of atoms. So this is something interesting. It would be not complete discussion if we cannot introduce impurities, because impurity is an important part of any real crystal. So how we engineer impurities in our ideal crystal, which is based on optical lattices, that's an important requirement to visualize, to simulate, to realize a real crystal at a larger scale, at a larger scale using cold atoms. We engineer impurities by introducing uh, external forcing, external periodic forcing on these atoms. So that's a very interesting way of simulating the impurities in a real crystal, but on optical lattice. So this is a very interesting observation, that if these optical lattices are being subject to external forcing, so we shake them periodically, so the impurity effect can be injected into the setup. So our system can behave just like an impure material. So for that reason, we are in a position to mimic various different characteristics which are seen in the real crystals. For example, in condensed matter physics, we know something as Anderson localization, which is very much useful and seen for an electron. Once it passes through a real crystal at impurities, it observes localization, because the periodicity of the structure, periodicity of the lattice is broken at that point. So it is localized. So the same thing we observe for atoms in optical lattices in the form of dynamical localization, because if we introduce an external force on these periodic lattice, so the atoms start presenting themselves as dynamically localized, which is mathematically proven and a log of Anderson localization. So this is the same property. So it's a very interesting way to engineer uh, impurity effects in an ideal crystal, what we see here. So this opens up another area, entire new area of discussion and innovations, because now we can make our crystals at a very large scale using ultra-cold atoms. And it is having more control and more flexibility. So this is something which is very interesting. At the same time, this discussion also takes us towards something as chemistry at ultra low temperatures, because if in addition to bosons, we have fermions, and these fermions can interact with each other, so they can make some newer crystals at very low, ultra low temperatures, newer chemical materials, and so on. So these are very fascinating areas once we enter into the discussion of bosons and fermions interacting together in one optical lattice, or fermions and fermions sitting together in optical lattices, and how they will be affecting each other, how they will be coupling with each other. So these stable couplings, ordered couplings, stable states can engineer newer state of matter, newer materials, better to say, at very low temperatures. So this is something which is again a very beautiful area, because we can engineer something which is not seen any time before. There are only stable state of matters, or there is stable state of compounds which are only available at ultra low temperatures, not any other scenario. So this is a beautiful way of seeing a chemistry at work at ultra low temperatures with the help of, again, our ultra cool atoms. So a huge big word is sitting here, which is reason of big excitement of latest discoveries in our present day time. We see many things coming up, and we will see many things coming up in future, because this work is uh, really getting the people like crazy. So here I will be giving a list of a few other areas which we have not discussed here because of limitation of time. And I'll try to introduce something maybe we have discussed already, that using ultra cold atoms, we can have the whole new subject of quantum metrology. What is quantum metrology? That we can develop sensors, or we at very high accuracy. So here we can have quantum clocks, for example, using ultra cold atoms, which can give us time with best accuracy. And this is a very beautiful subject of discussion. Many countries are now claiming to have their own ultra cold atom based clocks. and they can be developed in various different ways. They have various different configurations, and we use still ultra-cool atoms. In our work, in my laboratory, we have engineered our own method by which we can develop clocks at the ultra low temperatures and using and still performing far better than existing devices. And then we have, I just mentioned, ideal solid state systems, and many body effects can be discussed in these ultra cold atoms with the help of optical fields. And then we have quantum simulations. Quantum simulation is a big word because we try to develop anything at a very small scale, like atoms, like crystals, at a very large scale, using ultra-cool atoms. So this topic we have been discussing in our previous webinars as well. For example, when we were talking about nanofibers and the confinement of atoms around the nanofibers using optical fields, we were observing the atoms observe potential, which is very much similar to hydrogen atom potential seen by the electron. So that means we can generate artificial atoms using ultra-cool atoms around nanofibers. So now an ultra-cool atoms around a nanofiber is a huge big system, but you observe the same potential which is seen by the electron in an atom, like hydrogen atom, which is very difficult in many scenarios to control. Well, in present day experiments, we have been doing lot of good work using hydrogen atom and hydrogen-like atoms. But still, if you can do the same thing at a very big scale, with very good control, you can do lot many newer things, newer physics and technology and devices and so on. One other example I gave you when we were talking about atoms coming under gravity and reflecting back from the mirror. So in the vertical direction, the exponentially decaying field of the optical field and the gravity combined together make gravitational cavity. Now that gravitational cavity is also acting like an artificial atom. But the difference was that this artificial atom is not having continuum. That simply means that any higher you go in energy, you still find energy levels. Because continuum means that if you go higher in energy, you will be free from the potential at some energy level, at some energy. Just the same, just like an electron observe once it is given a high amount of energy, it parts away from the atom. It goes away. It's a free atom. The same thing we were discussing about a nanofiber and an atom rotating around that. If you give large amount of energy, it will dissociate from the nanofiber. So that is a continuum. It will be free. But now if we have exponentially decaying field all the time present, and then there's a linear potential, that's again acting like an artificial atom. And if this system stays, so then that artificial atom will be always there. So you will always find some confining energy levels. So this is something very interesting way to develop your very small system. I would not say them as nanoscopic. It's very, very small system at a very, very large scale, and then do whatever you want to do, and all good work at a very large scale. Once you have at large scale, you have better control, you have better configurations you can make. So this is the advantage. So and then we have Floquet engineering. Floquet engineering is basically once we have these atoms in some confined potential, and then we apply some external forcing, periodic forcing. So now that external periodic forcing becomes very much the same as atoms seeing a periodic force in space, periodic potential in space, like optical potential. But now this optical potential is not there. It is only periodic potential in time. Fine. So what is going to happen? These these atoms, ultra-cold atoms, once they observe periodic forcing in time, they will be developing newer state, bound state, like Floquet states, we name them. So they have newer energy states. Their energy spec. So energy is no more a conserved quantity, but when we solve this system, we get quasi-energies. And those quasi-energies are the Floquet energies, we say them. So these Floquet states become newer state of the matter in which they can survive as eigenstates. And then we can use them, as I was using the word, as flying qubits yesterday. So we can have these flying qubits in our control. So we have them here. And then I already introduced quantum chemistry, that we can develop quantum chemistry at nanokelvin or microkelvin scale. We can develop newer kind of materials combining fermions, boson together, and those newer kind of um, uh, materials would be seen only at that particular temperature, nowhere else. And then I also introduced yesterday that these techniques can also be applied on macroscopic scale. For example, we can use membranes instead of atoms, and then see how optical force modifies the dynamics of a quantum mechanical membrane, and what changes we observe, how many newer control comes in. If it is a de Broglie wave, so how the de Broglie wave is going to be modified. And these systems combined with our uh, our um, quantum computers give us very high storage efficiency. So this is something which we have done very recently. So combining nano electro-optomechanical systems with quantum computers based on ultra-cold atoms, we can achieve very high storage efficiency. So that simply means that we are in a position to store quantum mechanical information in the form of qubits with efficiency as high as 100%. So this is not achieved in any previous work so far, to our understanding. And then we have discussion of quantum AI and quantum machine learning. We are in a position to develop, using ultra-cold atoms, newer algorithms which can be used for ultra-cold atoms and so on in machine learning. So I'll stopping here, and I'll wait for any questions you have. And the discussion is definitely not stopping here. There's not many other things we can talk about, and it's a long list. We can still extend this. So I'll wait for your question and I'll try to answer them. Thank you.
Sir, I have a little question about the optical lenses. A little question about the optical lenses. I don't know, it may be a silly system, but when we have to simulate any crystal and we have to engineer any type of impurity in that crystal, how do we know about the specific impurity that crystal should have or
Okay, you see, uh, uh, well, as I understand, impurity cannot be on demand. Impurity is something which we want to avoid, and we pay a lot of cost to have pure crystals. Fine. So I'm simply conveying that impurities are unavoidable in real crystals. Now, if you want to have real crystals, effects seen in our ultra-cold atoms, so we need to engineer impurity some way. Fine. So now impurity in our optical lattices can be engineered if we apply a force, periodic force on these atoms. Fine. So this becomes a good way of engineering. Now, how much, the question comes, how much is the impurity? It's less or more. What is our requirement in our conventional discussion? We require ideal crystals for any use in a watch or anywhere, any sensors and so on and so forth, but they're very expensive. So here they're coming for free because they are optical lattices by definition. They're periodic. There is no way to break. So we break the periodicity by inducing external forcing. And if the force is more, the amplitude of external force is more, we may see that the impurity is more, or the prototype of impurity is more. Fine. And that we can see. For example, that we can measure in the form of localization of the system as dynamic localization. It's less or more. Well, any questions?
Virtual participant sir, he is question, Ms. Siddiq. Impurities are engineered by applying optical forces or lasers.
Okay, there are some other questions at top. There is a question that kindly elaborate to have 100% quantum efficiency. Okay, now when we want to talk about 100% quantum efficiency, we can say this is an ideal scenario. 100% quantum efficiency simply means that we send a data in the form of bits or qubits, and it is stored. And that would be our requirement. We should not lose any information. And whenever we want to retrieve it, we should retrieve it as such. So this is 100% efficiency. We have this surety to a good extent in our conventional computers. We open our data and we don't have any understanding or expectation that it's lost even to the small fraction. That will be a cost from our side. We don't have a good, we will not rely this kind of computer if it is losing the data. We don't want to use it. So in our previous discussion, where we want to have schemes or methods or ways to store quantum efficiency, the storage efficiency was up to 50% in one case we are studying in the absence of any optomechanical effect. But once we introduce optomechanical effect, so that increases to 100%. So this optomechanical effect introduces some conceptual changes into the system, and so in a very simple in a very simple way we can understand this, that the presence of optomechanical device introduces a locking of the information into the states. So because states have to store the information as 0 or 1. So if our excited state is 1, ground is 0, so we see that after a certain time, the excited state will be lost because of spontaneous emission. So that is the loss of data. We don't want that. But if we apply what we have seen, what we have shown, that if we apply an optomechanical setup over this qubit, so it is acting like a locking of the state. So that simply means the lifetime of the upper state increases many folds, and that increases the possibility of storing the data for a longer time. So that I'm reporting here. Thank you.
Okay. Thank
Okay.
you so much, sir.
There is another question.
Yes.
I go.
That is by the Mr. Siddiqui, and he is asking, kindly elaborate to have 100%
I answered this.
efficiency.
I answered this.
Already? Did
Yep.
it?
Okay. The second, that is the impurities, that is also answered. No, okay. That is also by Mr. Siddiqui, and he is asking, impurities are engineered by applying optical forces, lasers. So,
Okay. Well, I think I have answered this partly. I can come back to the same question again. That okay, we are introducing the impurities by applying external forcing. Now that external periodic forcing would not require any laser now. We can use only optic modulator in incoming lasers, and that can introduce modulation in the laser, and that can act like a periodic force on the atoms.
thank you so much, sir. Let me check if anybody else have a question. So please feel free to ask from us, sir, in a chat box. Okay, thank you so much, sir. Sir, please, I want to give you another introduction of a sir for today's webinar lecture series. So,
So
yes, you can sit it, and I will need your signatures for a certificate, and I will give you the again a brief introduction of your, because some of the participants are not know that much because they are not present first day. So yeah, please burden me for that. Thank you. Okay. Yes, sir, quickly. Okay. Like most of the students that are not present in the first day of lecture series, optical forces on atoms. So I just give you the brief introduction of Dr. Farhan Saif. Dr. Farhan Saif served as the chairman of the Department of Electronics, Quaid-e-Azam University, Islamabad, and he is the founding head of the Department of Physics, National University of Science and Technology. He obtained teaching and research experiences at the University of Ulm, the University of Arizona, the University of Sao Paulo, and the University of Electrocommunication, Tokyo. Dr. Saif, his PhD degree from the University of Ulm, Germany in 1998. He also served as a tenured professor in the Department of Physics at Quaid-e-Azam University from 2016 to 2018. And Dr. Saf research area, because mostly of people are interested in knowing the research area that is on the ultra cold atoms and in optical fields, quantum computations, quantum information, nano optomechanics, nano devices. Nano devices is very related to the biotechnology students nowadays and very high topic. You can take a help from sir. Quantum optics and dynamical systems. And with that sir has also have some national and international awards, including Satara Imtiaz, Pride of Performance, and Abdul Salam Prize, the World Academy of Scientists Award. He is a Fulbright Fellow Scholar as well. So thank you so much, sir. Thank you so much for your time. Today. Thank you. Or at the end of the today